Okay, let's pick it up where we left off. We just did some derivatives of the general logarithms. Let's move ahead. What is the derivative for a to the x? So any exponential, any number raised to the x power, right? Obviously, we know e to the x. What will it look like for any other number raised to the x? Turns out e to the x is the special case, the nice one. Okay, what's going on here? So we're going to start with this true statement, the log of a to the x with base a. And we notice we're using the same base in the exponential and in the log. So this would simplify to just x, but we can use this to our advantage. We take the derivative of both sides, like so. Okay, so we're going to use the rule we just learned to figure out the derivative for any exponential. Wow, genius. All right, what would it look like on the left? So the rule we just learned was, okay, take 1 over and then put whatever occurs here, right? This is like a chain rule, right? 1 over this part times the natural log of our base. Just show you here, and we've got some more, but let's talk through it. Okay, so the derivative of the outside, 1 over what appears in the parentheses, a to the x, times the natural log of this base here, a. Of course, then we still need to multiply by the derivative of what's inside those parentheses, a to the x. We don't know what that is. That's the whole point. We're going to end up solving for this in just a second. All of this is equal to the derivative of our x on the right side. Well, that's just 1. And look at this. I mean, we have it right here. Once we get to this statement, now we can multiply both sides by this denominator, and we got it. The derivative for a to the x is equal to a to the x times the natural log of a. So we see that same theme, kind of like e to the x, where it repeats, but then also tack on the natural log of whatever that base was, which is like exactly what we did for the general logarithm, right? 1 over x, but then be sure to multiply by the natural log of a in the denominator in that one. Okay, so fun. All right. Let's look at a couple examples, starting off real simple. F of x equals just a to the x, just some other number other than e raised to the x power. All we got to do is follow our rule. Hey, if our base is 8, then our derivative here is 8 to the x times the natural log of 8. Again, you see it repeats itself, but then be sure to multiply by natural log of the 8 as well. Let's take a look at a chain rule. How about g of x equals 2 raised, and the exponent on the 2 is x cubed plus 3x squared. Hey, it could happen. And if it ever came up, we'd want to be able to take the derivative of that. Okay, let's see here. So our base is 2, but we have obviously, a chain rule happening. So this x cubed plus 3x squared, that is inside the exponent of 2. The 2 is the outside function. So how's this derivative going to work? Well, our new rule tells us how to take the derivative of the outside. We're going to repeat the whole thing, right? Then we're going to simply multiply by the natural log of the base. So all of this gets repeated times the natural log of the 2. And there's the derivative of the outside. Then we need to multiply by the derivative of that exponent. And because there's more than one term, we need to use parentheses. So it's times 3x squared plus 6x. And there we have it. I don't think there's really anything to simplify there. Let's just leave it like that. Wow. Okay, again, what happened? We repeated the whole thing. But then, because we've got a base 2, we need to multiply by the natural log of 2 to get that derivative of the base 2 here. And then, of course, multiplied by the derivative of your inside. Okay, let's go back to my paper really fast. So we now know the derivative for e to the x is e to the x, and we just learned derivative for any other, well, not any other, any number, including e, is a to the x times the natural log of a. Hey, would this formula still work for e to the x? You know, it should. They should be consistent. If I thought of it like this, just where the base was e, right? I'd repeat e to the x, but then look, times the natural log of e. But again, that's 1, and it just boils down to e to the x. Wow. Okay. Back to the lecture. Okay. Moving on. There's one last piece to this section. We've done a lot of examples. We've discovered 3 new rules. So most of the homework is going to be focused on that. This one last idea is really interesting. Logarithmic differentiation. It turns out logarithms have some properties. Sometimes we call them the laws of logarithms. One of those is right here on the screen. We're going to take advantage of this fact about logarithms. You may remember this, the log of, say, m raised to the r, where there's an exponent. We can move that exponent down to the front, and that's equal, it's equivalent to the original. And, you know, it almost moves like moving that down to the front, you know, it kind of feels like the power rule, like a derivative. It's not. These are just equal. You may remember this from learning about logs in the past. Why would that be an interesting property of logarithms? How are we going to take advantage of this? We're going to be able to do derivatives of things like what you see here. How about y equals x plus 1 raised to the x, where x is both in the base and in the exponent. We have a variable in the base and a variable exponent. We've never done anything like that. No, we've done, you know, x plus 1 to the 3rd power or something, you know, just where the variable was in the base. And now we just learned how to do an exponential where we have a number raised to the x. But what if you have both of them? And it turns out if both the base and the exponent are variables, that's a whole new situation. None of our rules would apply to it. We got to think of a different approach. So we can do something like x plus 1 raised to the x. And of course, you see just below it, how about y equals the sine of x raised to the square root of x? Wow. Why would this rule help us to take advantage? Because we can move an exponent down in front. By cleverly applying logarithms and doing it very strategically, we're going to be able to move these exponents down out of the exponent. Let's check out the first one. I think we can fit that in. Let's look at y equals x plus 1 raised to the x. Right here. Find dy over dx, the derivative, using logarithmic differentiation. We say, part A, y equals x plus 1 raised to the x. Okay, here's what we're going to do. We're going to begin by taking the natural log of both sides. We can't do anything without that. We need to apply logarithms. Okay? So we got the natural log of y equals the natural log of x plus 1 to the x. Why the natural log? Because it has the nicest derivative. of course. Okay, once we do this, now notice we can apply our rule here on the right side. We can move this x exponent down to the front. X natural log x plus 1, like so. At this point, now that it's out of the exponent, we can take the derivative of both sides. Differentiate both sides. Notice that on the left, it's going to be implicit. Because it's the natural log of y. Okay, let's see if we can do that. Starting on the left, the natural log of y. So that derivative implicit would be 1 over y times dy over dx. Okay, there you go. There's our implicit differentiation for the left side. The derivative as normal, but then multiplied with the derivative of the y, dy over dx. On the right side, notice we've got a product. So we need product rule there. Derivative of x is 1 times natural log x plus 1 plus x times. Now here, the natural log of x plus 1, that's a chain rule. So it's going to begin with 1 over, and we got to put 1 over that entire thing, right? 1 over x plus 1. Then we'll multiply by the derivative of the x plus 1. That turns out to simply just be 1. Okay. Let's clean it up a little bit. This is the natural log of x plus 1. Here, I'm going to say this is x over x plus 1. We're getting really close. In the end, we need to isolate the dy over dx, right? So I'm going to multiply y over to the right side. Y times, I'm just going to put a big set of parentheses, all of this. Don't bother distributing the y. This is perfect. Okay, it's looking pretty good. We got dy over dx isolated. There's one issue. We'd really prefer this to be in terms of only x. We have this y here. What we started with was a function. We'd really like to know the derivative just in terms of x. No problem. Check it out. We got the y, but we know what y equals. So we can replace that y with this whole thing. Dy over dx will equal x plus 1 to the x times natural log x plus 1 plus x over x plus 1. And we did it right there. There you go, just in terms of x. Now, this is kind of interesting again. I kind of notice some of the patterns. The original function 1 plus x to the x, the derivative repeats that, just like an exponential derivative would. Repeats itself. Then it's got this other stuff based on the product rule. And that's the way it unfolded. So I don't know, there's really nothing to mention there, but the fact that it repeated itself was pretty interesting. Okay, let's do part B in the next video. See that